Hello. Oh. Okay. Okay. Okay, I'm just checking. How is the audio? Oh. There we go. How is the audio and everything and the video? Video is fine. Is it that there's background noise, or is it also, is the connection bad? Anyone who... Huh. Okay. Okay. Okay, just a moment. Okay. Oh, so I guess so for some people, the video is a bit pixelated. For some people, the audio is not too good. Let's just try this for a little bit and see how it goes. If things don't improve, well, let's hope they do. But, you know, oh, why did we switch from BBC? I was hoping that this Zoom, the connection would be, the audio would be better. It seems like it's not really better though. So in that case, we'll probably switch back, you know, but I wanted to try. I see. But we're gonna try it. Also, just a quick note. This is just for temporarily. I'm just using the free version of Zoom, so we have to keep it to 40 minutes long. I am talking. I don't know why you might not be hearing. Yeah. Okay. Okay, let's try it. We'll see if it's better or worse as we go. Okay. So today, just for the time we have, I wanted to do some of the examples. Just examples from the assignment. Just a moment. Okay. I'm not sure what you mean by can you turn back by the time? Okay. Okay. Oh, the previous screen, just so you know, is, I'll turn back, but this is just the end of the previous lecture, but I'll still turn back. But this is an old, where we were before, nothing new here. Okay. Okay, let's try okay. So let's try one of the induction questions. This would be question, let's try question 3B. No, let's try question 3A. Yeah, let's start with that. I'll write it down. Okay. It says n is an integer. Prove that there exists p prime, p divides n. Okay. And we're supposed to use induction for this. Okay. So so for integers n greater than 1, let p of n be there exists a prime p with p dividing n. Okay, and we have to prove this p of n for all integers greater than 1. Okay. And to do this, let's use strong induction. Okay, I have strong induction written down before. Let me just turn back to it. Let's see, where is that? Okay, here's strong induction. strong induction says if some condition, then this, well, this is the thing we want down here. So we have to show that this condition holds. Okay. So what we have to show, oh, see more, another person. Okay. So let's just adjust it a little bit. Let's go back. Here we go. We have to show that for all k, let's say, greater than or equal to 2, if P of 2, P of 3, up to P of k minus 1, then P of k. Okay, let's unravel what that means. Okay, so we'll just do a little what does that mean? It means we have to show the following list of things. First, we have to show that if k equals 2, this list is empty. So we have to show if nothing, then P of 2. That means we have to show P of 2. And then when k equals 3, we have to show that if P of 2, then P of 3. And then if k equals 4, we have to show that P of 2 and P of 3 implies P of 4. Okay, and we have to keep on going like that. We have to show that P of 2, P of 3, P of 4 implies P of 5. We have to keep on going. And then once we have shown all of those properties, then we are allowed to apply induction to conclude that for all n greater than 1, there exists a prime P such that P divides n. Okay. So easiest thing to do is to check P of 2. P of 2. That's the statement that there exists a prime dividing 2. Well, 2 is prime. Its only positive divisors are 1 and 2, so it is prime. And 2 divides 2. Why is that? Well, 2 equals 2 times 1, right? So there's an integer, in this case 1, such that 2 times 1 equals 2. So 2 divides 2. Okay, so 2 is divisible by a prime. That's P of 2. So that takes care of P of 2. Now, let k be bigger than 2 and assume P of 2, P of 3, all the way up to P of k minus 1. Okay, and now what we have to do is show P of k. Let me write down our assumptions again at the top. Assume k is greater than 2 and assume P of 2, P of 3, all the way up to P of k minus 1. And then our goal is to show P of K. That's what we have to do. And we're allowed to assume all that there's a prime dividing 2, a prime dividing 3, a prime dividing 4, and so on up to P of K minus 1. Okay. Okay, so now we must show that there exists a prime P that divides N, or sorry, that divides K. If we do that, then we'll have shown P of K and K, then will have shown that, you know, P of 2 up to P of K minus 1 implies P of K for all K greater than 2. And we also showed the same is true for P of 2, so we'll be done. Okay, so that's our goal now, is to find a prime divisor of K. Okay, so now either K is prime or not. Okay, if K is prime, well then K has a prime divisor itself. So K divides K for K prime. So P of K. And that is what happened with 2. You know, 2 was itself prime, so it definitely has a prime divisor itself. And that's what is going to happen, you know, part of the time. Okay, so that's kind of like the easy case. Okay, the other case is that K is not prime. Okay, what does it mean to be? Well, what does it mean to be prime? It means your only positive divisors are 1 and yourself. So to be not prime means you have another divisor. Okay. There exists L dividing K such that L is strictly between 1 and K. Right? Because K has more than 2 divisors, so, you know, 2 of them are 1 and K, and there's something else, maybe a bunch of things, okay? So take L to be one of the prime divisors. But then we've assumed that P of 2 all the way up to P of K minus 1 hold, so in particular P of L holds. And we can say by induction hypothesis. So P divides L for some prime P. Well, if P divides L and L divides K, then P divides K. This is because the divides is transitive. So in that case, P of K also holds. Okay, so in both cases, P of K holds, and that concludes the induction step. So you can say this finishes the induction step. Okay, now by induction P of n holds for all n greater than 1. In other words, every integer greater than 1 has a prime divisor. So we might as well write that. There exists p dividing at the end. Okay. And another fun thing you can do is to try and prove the same statement, but use the well-ordering principle. So let me write that down. Okay. If you don't have to, but you know, as practice, try using the well-ordering principle for that question. Okay. And what is, let me remind, well, the well-ordering principle just says that every non-empty subset of positive integers has a least element. Okay. And okay. As another example, I wanted to do maybe part of question 7. It just says, oh, that is a good question. Well, let me answer your question before I move on to question 7. So for the benefit of the recording, the question is from Joshua, which says, is it necessary? Okay, I'll turn back while I read this question. Yeah. Okay. So is it necessary to show a base case when using strong induction, since the base case will be covered in the inductive hypothesis? So that is a good point. The key is though, the reason why I did 2 separately, because we do have to know that 2 is prime. In the induction step, we're able to deal with either case, that the number is prime or composite. But for 2, it's very important that 2 is prime. If it's not prime, then things will kind of break down. Right? Yeah. But it is a good point. We did kind of do the same argument twice. So we only really need induction for the case that the number is composite. Okay. Okay, I'm going to turn the page. Okay, so let's compute I of 18. So solution, let's remember what the definition is just the number of A such that A is between 1 and 18, and the GCD of A and 18 is 1. It's the size of that set. Okay. I may have done this in class, but it's okay. Let's just do it again. Okay, so we just write down 1, 2, 3, 4, 5, 6, 7. Okay, and we'll cross off things which have GCD with 18 that's bigger than 1. Of course, the GCD of 18 and 18 is 18. Okay, so we can cross off 18. The GCD of 2 and 18 is 2 because, right, the greatest common divisor of 2 and 18 is 2 because 2 divides both. That's as big as it could be. And actually, any multiple of 2 will also have GCD at least 2. So I can cross off all the multiples of 2. Some might have a bigger GCD, but definitely these things will have GCD bigger than 1. Similarly, 3 divides 18. So the GCD of 3 and 18 is 3. And similarly, for any multiple of 3, we'll have GCD at least 3. So I can cross off all the multiples of 3. Okay. Now, actually, everything that's left has GCD 1 with 18. So let me just circle everything that's left. There's 6 things. The GCD, or sorry, phi of 18 is 6. We can call that solution A. Of course, we also have formulas for phi. Well, 18, that's just 2 times 3 squared. And 2 and 3 are coprime. So I can write it like that. This is since the GCD of 2 and 3 squared equals 1. And phi of 2 is just 1. And phi of 3 squared is just 3 times 3 minus 1. That's just 6. And then here we use a formula that the phi of p to the a is p to the a minus 1 times p minus 1. Okay, so that's the second solution. Of course, we see we get the same answer. Well, that's good. Okay, now let's write out the multiplication table for, let's do question 8. It's related to this question. Question 8. We have to write a multiplication table for u of 18 And in case you don't remember, that just means the integers mod 18, the ones that are co-prime to 18 under multiplication. Okay. So if we take these 6 things, we can multiply them together and work mod 18. So let's see what we mean. Okay, so we are working modulo 18. That means, well, you can kind of think of it, we can drop any multiples of 18. You know, so everything is mod 18 from now for the rest of this page. You know, 5 times 5, it's really 25. But I can drop an 18, right? So that's really 18 plus 7. That's 7. This is mod 18. And instead of putting equals, we usually have 3 lines. Okay. So mod 18, 5 times 5 is really 7. Okay. So if I want to start my multiplication table, I can do that over here. Okay, so 5 times 5 is 7. Of course, 1 times everything is just the thing back. Okay. What about, so let's record our scratch work over here. What about 5 times 7? That's just 35. And again, we have to drop an 18, so we get 17. So 5 times 7 is really 17. About 5 times 11, well, it's just 55. Again, that's 3 times 18. 3 times 18 is 54, so plus 1. So that's 1 mod 18. 5 times 11, that's 1. In other words, 5 times 11 is the identity of the group. So 11 is the inverse of 5. Okay. So 5 times 13. Well, that's 65. That should just be 11, just 10 more than 55. So it's 10 more than 1. Okay, so 5 times 13 is 11. And the one thing I'm missing is 13. So 5 times 17 should be 13. And here we can see a little trick. There are many. Well, 5 times 17. 17 is really the same as -1 mod 18. Let me finish this row of the table. I just now saw that there's a question. Let me finish this one row. Okay, 17 and -1 mod 18, those are the same. So 5 times 17 is really -5. And -5 is really -5 plus 18, which is 13. We get to see a 13. Or you can just compute it directly. You know, you get 5 times 17 is 85. And then I guess 72 is a multiple of 18, so you get 13 left over. Okay, and now there's a question. So for every table using prime numbers till the modulo number, that is a good question. It certainly seems that way. But you'll see let me just do some scratch work down here. This is we're just like to find the numbers. What we did was go between 1 and, in this case, 18, and find all the things which share no common factors with 18. It just so happened that the numbers which shared no common factors with 18 were all prime, but like we could just have to, that's not always the case. Like for we could try like for n equals 7, the things co-prime to 7 you know, the things co-prime to 7 will be all the numbers from 1 up to 6. Okay, so again, you get 6. This is 5 of 7. So it is just a coincidence in this case that all the numbers turned out to be prime numbers. It's not always the case. Okay. And then we could, you know, continue to fill out the table. Of course, the table is symmetric in this case. So now we get 7 times 7. That's, I guess, 13. I guess that should be 5. That should be 1. No. Anyways, yeah, that should be 1. And this should be 11. Right? Okay. We have probably enough, just a little bit more time. Actually, I saw a message that said that for this one-time Zoom won't stop the meeting after 40 minutes. So we just have time for one more question. So I'll just do question 1A just quickly. So we have this function. This takes a fraction and does 3s over r squared. Okay. And we are asked, is this well defined? Okay. So solution. So if it is well defined, we have to explain why, like with a proof. And if it's not well defined, well, I have to give you a rational number and like two different possible values using this definition. So one way to do that might be, the rational number 2 over 1 is the same as the rational number 4 over 2. F of 2 over 1 just says 3 times 1 over 2 squared. That's 3/4. And f of 4 over 2, well, that does 3 times 2 over 4 squared. That's 6 over 16. That's not f of 2 over 1. Okay, but 2 over 1 is the same rational number as 4 over 2. So f is not well defined. Okay. Okay, so we see an example where the function is not well defined. Okay, and I am going to stop there. Oh, I see a question. How do you prove a function is well defined? Well, we need to show, let me just briefly tell you. We need to show for part B, say, suppose R over S is the same as R prime over S prime. R prime, S prime are integers. S and S prime are both not equal to 0. Then you have to show, for part B, you would have to show that 3s squared over r squared is equal to 3s prime squared over r prime squared. Okay. When there's a question of whether a function is well defined, it means that we have defined our function in terms of like the representation of the input. So in this case, we've defined the function in terms of the particular numerator and denominator of the rational number. So there may be many choices of different numerators and denominators. We have to check that no matter which one you choose, you get the same function value. Okay, that means like in this case, we have to show that these two numbers are the same if R over S is the same rational number as R prime over S prime. Okay. So, yeah. Okay. So I guess we're gonna stop there. If you're having like if you want me to cover a specific question in more detail, I can do that. Just send me an email and I can probably make a video about it before Wednesday. If you need me to. Okay. So I'm gonna stop the meeting now. Also, please email me if you had a less than ideal experience with the connection with the audio or video. I also want to know that. Okay, so thank you everyone.